Okay, welcome back everyone. So let's start. Yesterday we discussed rumor spreading and first passage percolation on the complete graph. So today we are going to look at a different stochastic process, the voter model. We'll start with the complete graph and then we'll move on to more general graphs, and we'll also look at some variants of this model. So in the first part of the talk, I'm just going to go over a number of different models, and then we'll go on to look at how to analyze them and some results. Okay, so the classical voter model. So you have a collection of n voters or agents or whatever you want to think of them as, and each of them has an opinion or a preference in a finite set. So let's say just in the set 0, 1, it's a binary opinion. And then they interact with each other in some way and they update their opinions, and we'll see how they interact. And we can have models where they do this in either discrete or in continuous time. Okay, so let's look at the discrete time model in some detail. So we have n voters. And they all time goes in steps, and in each step they all simultaneously update their opinion. So there's a synchronous update, and what each voter does is independent of the others. They sample somebody at random, possibly including themselves, and then adopt the opinion of whoever they talk to. That's the model. Continuous time is very similar. So here the updates are asynchronous. Let's say each voter has an independent Poisson clock that rings after unit times, exponential 1 times. And every time the clock at a voter rings, they sample someone uniformly at random, again, including themselves, and then adopt the opinion of whoever they contacted. Okay, so what happens in this model in the long run? Well, this is a Markov process, whether in discrete or continuous time. And the states where everybody has the same opinion are absorbing, because then there's nothing else to change to, and you can reach these states from anywhere. So you are eventually going to reach consensus either on the value 0 or on the value 1. And the questions we want to address are: how long does this take? And what's the probability of reaching consensus on any particular value? And that will depend on the initial state. So how can you calculate that probability as a function of the initial state? Okay, so that was the question. So it's, let's give one concrete application to start with, which is in population genetics. So both the discrete and continuous time models are very well known here. So you have to think of the two opinions, 0 and 1, as two alleles of a particular gene. So let's call them little a and capital A. And we have some simplifying assumptions about how reproduction happens in the system. The population size stays constant. And in the discrete time model, it proceeds in generations. And then you should think of each child in the next generation as choosing their parent uniformly at random from the previous generation. And that's called the Wright-Fisher model. And in continuous time, again, population size stays constant. Somebody dies, and as soon as they die, somebody else is born uniformly from everyone and replaces that individual who's died. And that gives you that's called the Moran model. Okay. And both these are what are called neutral models for evolution, meaning that the two alleles, little a and capital A, have equal fitness. Neither gives you a fitness advantage over the other. And you want to know, just by random fluctuations, how does this population of alleles change over time? Yeah, they might. So those are statements about phenotypes, which gets expressed in the phenotype. And that doesn't matter here. What's important in the assumption is that whether it's recessive or dominant, it gives you no fitness advantage over the other allele. We will talk soon about what happens if there is a fitness advantage. Okay, so just for concreteness, we could again ask in the case of the, say, the Moran model, if you start with, if you start with a population of just type little a, and then there's a mutation and a single capital A arises, then what's the probability that eventually it replaces all the little a's? That's called fixation. And also, what's the time until either you reach fixation or this mutation dies out? You can ask questions like that. Okay, and so the next thing, you can again do this also for the right Fisher, but for concreteness, let's do it in the Moran model. So you can have selection in the model. So you have, again, the same setup, but now the mutant alleles, capital A, are favorable. They have higher fitness, 1 plus S. S is some small positive number. And now every time that some allele dies, they both die at the same rate, but new births favor the fitter allele. So you replace it with a copy of other allele chosen at random but weighted by fitness. So you're more likely to choose capital A alleles. Okay, and again, you can ask the same questions. What's the probability that it takes over the population, and how long does it take? There are other models. There's something called the infinite alleles model, where again, you start out with everybody being of the wild type. Now, every time there's a death, you get, each mutation is different. Every time there's a death, you get, with probability epsilon, you have a mutation of a completely new type. And then, let's say for the neutral setting again, where there is no selective advantage, over time you'll have different sizes of mutations of each type. So the mutations, let's call them 1, 2, 3, etc. So how many ones are there? How many twos are there in the population? So you can ask questions like that. So that we won't address that in this talk, but just to give you some flavor of the variety of models there are within this class of voter models. Okay, and then we'll move on to also looking at the voter model, not on the complete graph, but on arbitrary connected, undirected graphs G. So now the nodes of this graph again correspond to the voters. And so now how do they update their opinions when the sampling, earlier you were sampling uniformly at random from everybody in the population. Now you can only sample from your neighbors in the graph, and you might either choose uniformly at random from your neighbors and copy their opinion, or you choose non-uniformly according to some given matrix P, the probability of choosing different neighbors in discrete time, or a rate matrix, a rate of contacting others and copying their opinions in continuous time. So these generalize the voter model to arbitrary graphs. So in discrete or continuous time, this is the most general version you can think of. Okay. And if G is the complete graph and these matrices are chosen uniformly, then you get back to the classical voter model. And again, the questions are about consensus times and probabilities. Okay, so also, mostly we are going to be interested in what happens on finite graphs, but just by way of motivation, let me also talk about infinite lattices. And these were, I think, the earliest models to be studied, in fact. So you have a d-dimensional lattice, and you have some initial preferences. And again, you want to ask what happens in the long run. So we saw that in finite graphs, in the long run, we always reach consensus. Everybody becomes 0 or 1. And is that also true in this setting? Okay, and it turns out that it may or may not be true. It depends on the dimension. Okay, so that's the answer. So we'll see why we get this answer later. what happens is that in 1 or 2 dimensions, you do reach consensus, meaning that, okay, if you start with, let's say, only finitely many zeros or finitely many ones, one of them being finite, that thing dies out. Or you can start from arbitrary initial conditions, but you look at a large enough region, large finite box, and after some random finite time, it will always stay frozen at 1 or frozen at 0. In that sense, you do reach consensus, whereas in dimensions 3 or more, you have coexistence. You have both zeros and ones existing forever. Okay. And we'll see why this happens. Okay, and water models have lots of applications. So I talked about population genetics already. I believe the study of water models first arose in spin glasses in statistical physics as a kind of description of the Ising model. And they are used in biology. So you have the theme of choosing restaurants in Bombay was a very dominant one so far in the conference, but ants or bees also have to decide not which restaurant to go to, but which foraging site to go to. And they use some mechanism of reaching consensus for the whole colony to go and forage somewhere. And bioluminescent bacteria decide whether to express their luminescence or not, and that seems to depend on their density, and there's some form of quorum sensing. So even in extremely simple organisms, something like the water model seems to be going on. Okay, flocking is another example. And then economists and social scientists are interested in how do we choose between different products, which ends up deciding which of these products is going to be successful. The decision may be a bit more complicated than the water models we looked at, but they are maybe a starting point for thinking of these things. Here, these are examples where they arise naturally, but you can also use them as a basis. So to resolve conflicts in computer science, if you have distributed databases and there have been differences in updates between them, how do you reconcile the updates? And there's been some sudden upsurge in interest in this coming from blockchain. So there are situations where consensus is important to establish in these systems, and you might use something like a water model to do that. Okay, so that was various models and applications. So how do we analyze these models? So I'll use the board a little bit for this. So there's a classical graphical representation of the water model, and that's useful for analysis. So each vertical line corresponds to an agent, and time goes from top to bottom. So let's look at the continuous time version or the Moran model, just because it's easier. So there are random times at which, and okay, so they start with some initial opinions, let's say 0, 1, 1, 0, 1, and we want to know what opinions they end up with down here. We look at, there are some random times at which vertices contact each other and copy the opinion. The arrow shows the direction of contact. Okay, so there are, to work out what the opinions are at this later time. So time starts at 0 here and some later time, capital T. If I want to work out the opinions, there are 2 ways I could do this. I could follow everything forwards as time goes down and keep track of what happens whenever there's a contact. Or I could start at time T and work my way backwards. Okay, so what does this backwards in time process look like? So as I go back, the first arrow I see is this one here, and that says that this agent 2 has copied agent 3, which means that to know the final state of this agent, I don't care what agent 2 did before this time. So I'll put a cross just above this to say I don't care about what happened before this. All I need to keep track of is what agent 3 did, and so, okay. Similarly, okay, the next previous event is 4 copies 5, so again, I don't care what happened to 4 before this, so I keep track of 5. Okay, and then 4 copied, I don't even care about 4 at this point. I go to this arrow, 1 copied 2, so I don't care what 1 did before this point. Okay, so now if at time t, I want to know the states of the different agents, what I do is, let me do this for agent 2. I go from time t back to time 0. I can't go past a cross, but I can follow arrows. So I try to find a path from here back to there. So here's my path at agent 2. It goes up here. I can't cross that, so I follow this arrow, and I go all the way up to the top. So I copied agent 3, which had initial opinion 1, so I end up with opinion 1 at agent 2 here. Okay, so you have this backwards in time process. Okay, so we can do this for one agent at a time, but let's describe what happens to the whole population. And this is the way to describe it. So I'll start with a particle at every 1 at this time. And we go backwards in time. So here, 2 copied 3. So what I do is I move this particle from 2 to 3, and it merges with the particle at 3. So these 2 particles have fused to make 1 particle. 1 is still here, 4 is still here, 5 is still here. And then I keep going further up. Now 4 has copied 5. So the particle at 4 has gone to 5 and merged with it. It has no dependent existence anymore. 3 is still here, and 1 is still here. Okay, now I come to this arrow. There's no particle at 4 to move. I simply ignore this arrow. Now I come here. 1 moves to 2. There is no particle there to merge, so it just moves. Okay, and so what I'm left with is particles at 2, at 3, and at 5. Okay, and it so happened that these had the same initial opinion, so we have reached consensus by time t in this example. If in general we may not have reached consensus, but if we had been left with just a single particle at this time rather than 3 particles, then for sure we would have reached consensus no matter what the initial opinion is. Okay, so when we look backwards in time, what we have is a system of coalescing random walks. So because these arrows are drawn, say in forwards time according to exponential 1, then also in backwards time they are drawn according to exponential 1. So you can ask, if we have particles performing independent random walks where they are moving, so a particle at a vertex after x1 time picks another random vertex to move to, or a random neighbor in the graph setting, and all these particles are performing independent random walks, unless a particle moves to an occupied site, in which case it coalesces with the particle already there. And then the coalesced particle continues to perform this random walk. Okay, so that's the model of the water model backwards in time. Looks like this coalescing system of coalescing particles, coalescing random walks. Okay, so that's the representation that helps us to study the water model. The number of particles is monotone decreasing, yeah. No, it doesn't. So from x t, so if you know it at xs and follow it to the xt a later time, then backwards between t and s, it would be the same. No. So you start with something at time 0, you pick a last time you are going to look at, and then from that last time, you start your system of coalescing particles. You are assuming there's one particle at each site here. Now, if you wanted to pick a bigger T prime here and start backwards from T prime, then there may be even fewer particles already by time T. So you can't, so you can't construct T prime to T based on this. So you have to do it afresh, yeah. The question reminds me also of a connection. So this is very closely related to the Wilson algorithm for perfect simulation backwards in time. Okay. So there you start particles from different states and you look backwards in time to see if they have all coalesced. And if they have, then where they have coalesced gives you a sample from your Markov chain with exactly the invariant distribution. Okay, good. So where did I put this? Okay, so that's the coalescing particle representation of the water model backwards in time. We can use that to answer many of the questions I asked earlier. Sorry? It's a finite. Mostly it's a finite graph, but we can also answer the infinite lattice with this, using this representation, which I'll do just now. Okay, I think that's what I just did in pictures. So you have all these particles performing independent random walks in continuous time according to this rate matrix Q, or in discrete time according to a probability matrix P, and then they merge if they move to an occupied site. Okay, so what does this tell us? This tells us, okay, so if we were looking at the classical model, where particles move after independent x1 times, we can do a calculation which shows that the expected time to reach consensus is n. The coalescence time is in fact n, so the consensus time is smaller than n. By the coalescence time, I mean the time when all the backwards walks have met. That's exactly n in expectation, or n minus 1. The consensus time is the time when they all have the same opinion. Of course, you've started at some initial conditions. You may not need to get down to one particle. You might get down to some small number of particles and already reach consensus. T is the consensus time, and it's less than or equal to, and the coalescence time is equal to. Okay. For the continuous time model. For the discrete time model too, it's the exact same scaling. I don't know if it's also exactly n, but it's order n. It's the same. And so you should compare this n with the Rumours spreading model we discussed yesterday. If we scale the rate at which particles do something the same way, there the Rumours spreading time would be log n. So Rumours spread much faster than the time it takes to reach consensus. Okay, consensus is much slower. Okay, so I think I don't have time to do the calculation to show that, but it's very easy. So you just look at, so define times tau, which there are exactly k particles left, and you ask from k particles, how long does it take you to get to k minus 1 particles? And for that to happen, a particle has to move to an already occupied site of which there are k, and that's exponential. You can do the calculations, them up, and you get this. The intuition is roughly. So you can ask how many on the graph. You can ask how many zeros and how many ones are there. So if the number of nodes with opinion 1 hits either 0 or n, you have reached consensus. You start at some intermediate stage. You start with k of them having opinion 1. And then each time exactly one node changes its opinion, so you might end up going to k plus 1 or k minus 1, or you might stay where you are. There is equal probability of going from k to k plus 1 as of going from k plus 1 to k. Yeah, there's a drift in one direction, whereas this is diffusive, and that's why it's much slower. Yeah, exactly, yeah. Yeah, and the second implication we get from this coalescing random walk construction is that you have consensus in 1 and 2 dimensions and coexistence in 3 or more. And that's because if you look at, take 2 sites in your infinite lattice and look at the particles that started from those sites, they are performing independent random walks. And the question you want to ask is, do they ever meet? Because if they meet, then these 2 sites are going to reach consensus. And if they don't meet, then they don't. And in 1 and 2 dimensions, the random walk is recurrent, so any 2 random walks will eventually meet, whereas in 3 or more dimensions, they may not meet.
Interact with not a consensus stepwise interaction. An epidemic model would be a group interacting with one particle.
Well, no, at a time it's still a pairwise. At any given time, it's a pairwise interaction. But I think it's more the drift versus diffusion. There is a drift to the random walk, and or there's a region where there's a drift, yeah. And whereas here it's diffusive everywhere. I guess so. Yeah, I guess so. Okay, I'd have to think about that, but I guess so. Okay, good. Okay, we can also ask given the initial state, what's the probability of reaching consensus on some specific value, say 1? And there is some martingale for, from now we'll only talk about finite. And there's a martingale associated with this voter model. And you can check that it's a martingale easily, but I guess I don't know who thought of this first, but they have had talk in mind up with this guess for the martingale. So let's look at the random walk governed by this rate matrix or the transition matrix. And we are going to assume that it has a unique invariant distribution pi. If not, consensus is not guaranteed. There's something wrong with your graph, which is preventing consensus. So if you have this, let's say xt is the configuration of the voter model at time t, so it's a 0, 1 vector of length n. And you take the dot product of that vector with this invariant distribution pi, that's your m of t, and that is a bounded martingale. And you can apply optional stopping to that. And that tells you that the probability you reach consensus on the value 1 is the dot product of pi with the initial condition, x naught. So you get the probabilities as well. Okay, so that was easy. The coalescence time on the complete graph was easy. On general graphs, it's not it's quite hard and there are only some bounds. So basically we are left with how to study random walks on graphs and their behavior. So what can we say for this simple symmetric random walk where you choose a neighbor at random? Haseen and Peleg showed that on any connected graph, the coalescence time is at most n cubed log n. And this is in general the best possible, close to the best possible you can hope for, in the sense that there is a specific where it is as big as n cubed, and this is the so-called dumbbell graph where you have two big cliques of order n vertices joined by a long path of length order n as well. So this is somehow a bad graph for random walks to mix. They stay in one part of the dumbbell or the other, and that also takes a long time for coalescence.
Is that implication for the example?
I guess so, yeah. Yeah, for the mixing times of Mark chains would come in, I guess, in generating perfect samples as well.
Because I know that there are a lot of times something algorithm like on parameters. That's pretty good.
Yeah, so page rank, okay, there's another model called the Decoot model that I didn't talk, averaging model rather than consensus, and that's very close to, or maybe the same as page rank. Yeah, and that converges faster. So there is an eigenvalue gap that determines the rate of convergence of that. And in fact, there are bounds on this coalescence time also in terms of the eigenvalue gap, which I'm just going to show you, is in this paper by Cooper et al. So I have to define a few more terms to describe their result. No, actually, it's just here. Okay, so they look at the discrete time. Haseen and Peleg looked at continuous time. So you have your random walk matrix P, and lambda 1, its largest, its Perron-Frobenius eigenvalue is 1. It's a stochastic matrix. Lambda 2 is the second eigenvalue. And they assume that it's bigger than the negative of lambda n. So if your graph is bipartite or if there's something wrong with it, work with the lazy random walk, where you stay at each vertex with probability half and move according to P with probability half. And for the lazy random walk, lambda 2 is always bigger than minus lambda n. And so this determines the spectral gap of your matrix. There's another parameter that also plays a role in the coalescence time, and that's a measure of how skewed the degree distribution is. So nu is your mean squared degree divided by the squared mean of the degree. Okay. And that lies between 1 and n. So it's 1 for regular graphs and n for the star graph. And for power law graphs, it'll be like a fractional power of n. For Edershen graphs, it'll be a constant. Okay. So these two parameters give you your bound on the coalescence time. So that scales as 1 over 1 minus lambda. So 1 over the spectral gap times, there's a log to the 4n. This may not be optimal, but some log n to something is you would expect. And then there's this other thing that comes out of it's n over nu. Okay, so you have n squared? No, you have n. So the worst nu can be is nu is if n is if it's regular. If it's regular, nu is a constant. Yeah. So it's between n and 1. It's between n and 1, the second term. The worst the second term can be is n. If you have a regular graph or a fairly homogeneous degree distribution, this is a constant, so you get n. Yeah. Mm-hmm. And if your graph is an expander, then the denominator here is a constant. So the bound you get, n is the dominant term here. So you again get Et is bounded by a constant times n, which is what you got for the complete graph. It's quite similar in behavior to the complete graph. But the complete graph is not the best case. So the star is the best case. So on a star, you reach consensus very quickly. Nu is close to n. It takes constant time to reach consensus on the star. Yeah, yeah. Your eigenvalue gap is also big, so you reach consensus fast. Yeah? Laziness may not be essential, and they prove, but you can, if your random walk matrix is, if your graph is bipartite, then you can never reach consensus. Sorry? Eperiodicity is needed. I think they prove you may need 1 minus max of lambda 2 minus lambda n in general, but yeah, you can always reduce it to just looking at lambda 2 by considering the lazy walk. Yeah, he had the maximum hitting time of any vertex from any other. I think that was his bound. Yeah. Okay, so let me say a little bit about their proof. Okay, so corollaries, yeah, it's linear in n for expanders, and it's sublinear for some scale-free random graphs. Yeah, I won't go into detail. So just what are some ingredients in their proof? So they divide the analysis into two phases. They fix some k star, which is growing quite slowly with n. And they look at the coalescence time as the time to go from n particles to k star, and then from k star to 1. And they bound each of these terms separately. And for the first part, they look at how long can these k star particles avoid each other, and they can't avoid them for too long, so you'll get below k star by some time. And then in the second phase, you look at how long it takes to decrease the number of particles by 1. So for each k particles, how long does it take until any two of them meet? And to look at the meeting time of two independent random walks on a graph, out of k of them moving separately, you look at tensor products of graphs. So this is how you define them. So you construct a graph whose vertices are k tuples of vertices of your original graph. You put an edge between them. If each component v and w, there's an edge in your original graph. And you look at this so-called diagonal vertices where at least two of the components are the same. So if you hit some vertex, that means two of the random walks have met. Okay, and then you modify the graph a bit by contracting this set of vertices to a single vertex. So they do all these things in the paper, and then what they use is the fact that the spectral gap of your new graph gamma is at least as big as the spectral graph of original gap of your original graph. And then in this new graph gamma, you want to find the hitting time of this distinguished vertex little gamma. And to get bound the hitting time, how did this happen? Okay. Okay, this thing has, I've missed a couple of slides somewhere. Okay, never mind. So how do you bound the hitting time of this vertex? It's bounded by So you found the hitting time of this distinguished vertex, little gamma, starting from an arbitrary initial condition. So you split it as the mixing time from that initial condition to stationarity, and then starting from stationarity, how long does it take you to hit this distinguished vertex? And there are good bounds both for the mixing time in terms of the eigenvalue gap, and then for the hitting time started from stationarity from the work of Aldous and Phil. So they put together these bounds to get a bound on the hitting time of this distinguished vertex. Okay, so that gives you a bound then on the coalescence time or the consensus time on general graphs. So that's the work of Cooper et al.
How much time does it take to go from one consensus to another consensus?
You can't, because it's absorbing.
But with some shift, once you move away from the other.
Okay, so if you allow some noise that changes things, it takes, okay, on the complete graph, it's easy. You are going to come back. If you only move a little bit, you are quite likely to come back. So it's going to take you...
Again, condition on the fact that you don't come back.
Yeah. So it takes you time n to go away. And from small perturbations, your chance of escaping is 1/n. So you would come back n times, but you come back very quickly in constant time, and then take an additional n time to go across. So it's still n. It's linear in n to go to the other consensus. So can you repeat that question?
Like you have reached consensus, but there is an internal lifetime for each state. After particular exponential potential, you change into state. So in that case, consensus will not be stationary, right?
Yeah, so, okay, so your model is that voters spontaneously change their mind. Now it depends on how you scale this thing happening. So if I change my mind on time scales much smaller than the time it takes to reach consensus, then I don't think consensus will ever be reached. There will always be noise in the system. If it takes place on time scales much larger than the time it needs to reach consensus, and n times as long, then you can ask this question. So you have to wait until first you escape from consensus, and then you have this again random walk. So you can decompose it. It shouldn't be hard to answer that question. Okay, so that's that's all I wanted to say about this model of the voter model on general graphs. So now I want to come back to the Moran model with selection. I thought I had put this slide much earlier, but never mind. So back to the Moran model. So you have the little a alleles have fitness 1, the capital A alleles have fitness capital A. And n of t is the number of them at time t. And to start with, let's look at them on the complete graph. Then this quantity is a martingale, and you can show that you reach fixation. So the capital A allele takes over the whole population with some constant probability, depending only on its fitness and independent of the population size. So no matter how big your population, a single mutation can take over the whole population if it's fitter. S is the fitness difference. So long as there is a positive fitness difference, it can take over. Okay, and that's not surprising, because all you are saying is that a random walk with drift can go off to infinity with strictly positive probability. Okay, and the time to fixation is log n. It's quite fast. Okay. Not n, but log n. So this happens much faster, the same time scale as rumor spreading. And in fact, this result is, okay, so you can ask, okay, that's for the complete graph. What happens on general graphs? This is coming from the drift, yeah. What happens on general graphs, we don't know. But there's one special case that, and it seems hard because there are no martingales we know of for general graphs, and there's no, this random walk duality doesn't exist for when there's selection, so we don't know how to analyze this in general. But if you have regular graphs, then the exact same result as for the complete graph goes through. And the reason there is quite simple. So no matter what your configuration, the number of edges connecting capital A to a little a, so somehow the probability with which a little a samples a capital A and becomes a capital A is balanced by the capital A contacting the little a. So the edges from one type to the other type are exactly balanced. And so your random walk probabilities are exactly the same as if it were a complete graph. So they go through, and if the graph is close to regular, so the ratio of maximum to minimum degree is close to 1, then you can still push through this argument and show that fixation happens with strictly positive probability as n goes to infinity. Okay, so in 9 minutes, I might skip some of this. So let's talk about trying to reach consensus on the majority. So far I've just focused on do we reach consensus and not cared about which value we reach consensus on. But what happens if you want to ensure, so you have some initial condition and you want to ensure that you reach consensus on the majority value, and you want to, okay, you just want to do this with high probability, not with certainty, but you want to do it quickly as well and using decentralized algorithms. Can we do this? I'll skip this model, which was studied by Peron, Vojnovic, and Vasudevan. So they looked at a model where there are 3 states, 0, 1, and undecided. If I talk to someone with a different opinion, I become undecided. And if I'm undecided, I copy whoever I talk to. And they showed that in this case, the probability of reaching consensus on the minority value decays exponentially in population size.
What is the differentiate the graph about which graph and the given constraint will help you to like objective or more?
No. Let's start with the complete graph. It's the complete graph, but you want a different rule for the voter model. I don't just talk to one person and copy them, but I do something a bit more complicated. And one slightly more complicated thing to do is I don't change my opinion immediately. With probability, it's just a time change, so that doesn't help. If every time I hear an opinion, I change with probability half, then things slow down by a factor of 2, but nothing else happens. But if I hear a contrary opinion, suppose I become undecided. So that builds in some memory into the system. And then the next time I talk to someone, I adopt their opinion, then that has the effect of somehow biasing things and gives you this increased probability of, gives you a drift towards the majority. That's what you're trying to engineer, a drift towards the majority value. Okay, so they studied this model and showed that the error probability is exponentially decaying in the population size and depends how far your initial value is from half. If you're very close to 50-50, you are still very likely to make an error. But if you're far away, you do well. And D here is the relative entropy function. Okay, and yeah, so similarly, in some work with James Kruse, I looked at a variation of this. So what we do here is there are no internal states, but every time, instead of sampling one voter, you sample, let's say, 2 voters. So I ask 2 people for their opinion, and if they both agree, then I adopt their opinion. But if they disagree, then I stick with my opinion. And you can also generalize that. So you could ask M people and only change your opinion if some supermajority K of them disagree with you, etc. So you can pick, so you have a whole family of models parameterized by M and K. So in all of them, you get essentially the same result. So this is if K equals M. You again get error probabilities decaying in the population size. The relative entropy plays a role. And if M equals 2, you get back exactly the same result as the three-state model. For larger values of M, you have faster exponential decay and so on. And the time to reach consensus is log n. Okay, you can do things for M, for arbitrary M and K, you have similar results. I'll skip that. You can also randomize M and K. And in all these cases, you have exponential decay of error probabilities. Okay, and the proof for the complete graph is pretty straightforward, and it relies basically on noticing that what happens is a biased random walk. Away from the center, it's biased towards whichever corner you are close to. So that was for the complete graph. And again, the general graph version of this was studied by Cooper, Elsasser, and Racek, and a couple of different authors. And they looked again at the discrete time model, and what they showed was the following. So you can sample two neighbors either uniformly from your neighbors in the graph or according to a weight matrix, but you sample with replacement. So even if you only have one neighbor, it doesn't matter. You can sample them twice. All you need is for the graph to be connected. What plays a role, again, is the spectral gap of this random walk matrix, your degree distribution, so if you sample uniformly, the weights are the same as the degrees, otherwise it's the sum of the weights. So what matters is the spectral gap, the variability of the degree distribution, and there's this quantity epsilon naught which tells you how far apart your initial condition is. So A is your zeros and B is your set of ones. The total weight of the zeros and the ones should be somewhat separated. And then there are some other arbitrary constants. Delta and psi are small and K is big. And the main result is the following. So if your spectral gap is big enough, so if your second eigenvalue is far enough away from 1, so you have to be below 1 over square root 2, your initial populations are well separated enough by at least 2 lambda squared and some other condition in terms of the variability of the degree distribution, then all the things you want happen with high probability. So it reaches consensus in order log n rounds, and the larger weight wins. And so this result is useful on expanders with not too much variability, and on power law type graphs, you in fact have even faster consensus of log 1 over lambda. And again, the opinion with larger weight wins. With high probability, Both are with high probability, yeah. Okay, and this proof is quite involved. This may not be optimal. Maybe you can improve some of these, but it's quite involved, and yeah, I don't have time to go over that. Okay, so I'm done with 1 minute to spare.